Hello there, Mr. Sutton here with the 610 AB Calculus classwork solutions on rate in, rate out. On this no calculator problem, we have water pumped into an underground tank at a constant rate of 8 gallons per minute, and water is leaking out at a rate of radical T plus 1 gallons per minute. So we have a rate in and a rate out for 0 to 120 minutes. And we're starting with 30 gallons of water at time 0. So given that setup, first part of this, we want to know how many gallons of water leak out of the tank from time 0 to time 3. Okay, well, our leaking out function is this radical T plus 1 function here. So if we want to figure out how much leaks out over the first 3 minutes, then we need to integrate this rate of change from 0 to 3. So I'm going to say water out equals integral from 0 to 3 of radical T plus 1 dt. And because this is a no calculator question, I have to take the antiderivative and do this by hand. So this is really T plus 1 to the 1/2 power. That bumps up to a power of 3/2, and we're dividing by that, so multiplying by 2/3. So we end up with then 2/3 T plus 1 to the 3/2, all of that evaluated from 0 to 3. So to make my life a little bit easier, because again I have to do this by hand, I'm going to take this 2/3 outside, and I'm just going to do this T plus 1 to the 3/2 stuff inside a big parentheses. So when I'm raising things to the 3/2 power, I'm really square rooting and cubing. So this is going to be, let's see here, 3 plus 1 inside a square root, all of that raised to the 3rd power. And then I'll do essentially the same thing with 0. So square root of 0 plus 1 cubed, and we're subtracting. Now we've got, let's see here. This is the square root of 4, which is 2. Cubing that gives us 8. Over here, we've got square root of 1, which is 1, and cubing that gives us 1. So we have 2/3 times 8 minus 1. So 2/3 times 7, which is going to be 14/3. And that's in gallons because we asked again, how many gallons do we have that leaked out in this time? For this part, we want to know how many gallons of water are in the tank at time 3. So there's a few things to consider here. We have the initial amount that was in the tank at time 0, that was 30, plus they said that we're pumping water in at a constant rate of 8 gallons per minute. So we're going to integrate the function 8 from 0 to 3. So integral of 8 dt from 0 to 3, which we can very quickly figure out in a minute. And then we also have to subtract the amount of water that goes out, that's being pumped out or leaking out. So we're going to subtract the integral of this leaking out function here from 0 to 3. All right, so we have to go a little bit further. We can't just leave these in integral form. 30 is playing itself in this motion picture. How about the integral from 0 to 3 of 8? Well, this is essentially a rectangle with a base of 3 and a height of 8 all the way across. So that's just 3 times 8, which is 24 for that area. And over here, this looks familiar. Oh, that's right. We just figured this out on the last problem in Part A. From Part A, this was 14/3, and we are now subtracting 14/3. So this is going to be, let's see, 54 minus 14/3. And you can actually leave it in this form and just stick gallons on the end. But if you really wanted to simplify it, let's see here, a common denominator, 3 times 54, that's going to be 162 minus 14. That's 148/3 gallons if we actually simplify that down. For this part of the problem, they want an expression for A of t, the total number of gallons of water in the tank at time t. So again, we've got that initial 30 that we always have to factor in. And we're going to add the integral from, let's see, this was at time 0, so from 0 to t, because we want to pick the time. And then inside, we're going to have the amount in, that's this 8, minus the amount out, or the rate out, that's this radical t plus 1. Except we can't put t in there. We have to put a different variable inside the integral, so we're going to use x. So I'm going to write plus the integral from 0 to t of 8 minus radical x plus 1 dx. And if we wanted to, we could split this up a little bit to be 30 plus 8x, or actually I guess it would be 8t at that point, minus the integral from 0 to t of radical x plus 1 dx. For this last part of the problem, we want to know what time between 0 and 120 is our amount of water at a maximum. All right, so we need some critical values for this, which means we need the derivative A prime of t. Now, A prime of t, that's just going to be your rate in minus your rate out. So 8 minus the square root of t plus 1. And then to find some critical values, let's go ahead and set that equal to 0. So now if I subtract 8 from both sides, divide by a negative, I end up with 8 equals radical t plus 1, or I guess you could just add t plus 1 radical to the other side. Now to solve for t, we need to square both sides. Again, this was a no calculator problem, so we needed to use some algebra here. So 64 equals t plus 1. And then subtracting 1, we get a critical value of 63. Okay, so at this point, we've got a few ways we could go. One way is we could use the candidates test, plug in our critical value, and also the two endpoints, 0 and 120, into the a function that we defined in part C, and then figure out a bunch of integrals and pick the highest value. But since we have to do all of that by hand, that could take a while. So since we only have one critical value, another way to go is to do a little sign analysis and see if this is a local min or local max that we're dealing with. So let me do some sign analysis here. I'm going to put 63 on a number line along with my endpoints of 0 and 120, just so I don't accidentally pick values that are outside the domain. And I'm just going to pick a value between 0 and 63, like 1. If I plug 1 in here, this is 8 minus 0, which is a positive. And now I'm going to plug in a number between 63 and 120. And I'm going to be kind of strategic here. I'm going to plug in 80, because 80 plus 1 is 81, and the square root of that is 9. 8 minus 9 is a negative. So since I am changing from positive to negative here, since a prime is greater than 0 from 0 to 63, and a prime is less than 0 from 63 to 120, that means that we have a local max, and since it's the only critical value, it must also be an absolute max. Another way to think about it, if your amount of water is increasing until you get to 63 minutes, and then is decreasing after that, the only conclusion here is that you have a max at 63 minutes. For this problem, the overall setup is we have 700 people in line for a popular park ride when the ride begins in the morning. And let's see, people are getting on at a rate of 800 people per hour. The park closes 8 hours later. And this graph is showing the rate at which people arrive throughout the day. So we have a rate in and a rate out. We have a rate in to get into the line for the ride, given in the graph here. The rate to get out of the line and onto the ride is this 800 people per hour. It's a constant function. So for our first part, we want to know how many people arrive at the ride, so the amount in, between times 0 and 3. So for that, we're going to use the rate in, which is, again, given by this graph. And since this is just a graph and no function otherwise, to integrate this to find the amount of people who actually came to the ride, we just have to find the area under our curve between times 0 and 3. So we're going to say then that our rate in is going to be the following. So I'm going to say we want the integral from 0 to 3 of r of t, because that's the name of this graph here. And we have a trapezoid from 0 to 2. That's our first shape. So that's a base of 1,000 plus a base of 1,200 over 2. And then we're multiplying by the height of 2. And from 2 to 3, we have to use this other trapezoid. So base of 1,200 plus a base of 800, all that divided by 2, times a height of 1 this time around. And we could simplify this to see what it comes out to. Let's see, these 2's are canceling, so you've got 2,200. And then for this other piece over here, this is just 2,000 over 2, so 1,000. 2,200 plus 1,000, that's going to be 3,200 people arriving. For the next part of this problem, they want to know if the number of people waiting to get in line on the ride is increasing or decreasing between times 2 and 3. So if you just look at the graph here, you're like, oh, that's going down. But this is the number of people, this is the rate at which people are arriving. We have to keep in mind that the rate at which people get on the ride is only 800. It's a constant value of 800. If you graph that on the same graph here, you've just got a horizontal line at 800. And we notice here that between 2 and 3 at least, the r of t, the rate at which people are arriving, is greater than 800. So that means that there's more people showing up than are getting on the ride during that time interval, which means that the number of people actually waiting in line is going up. Now, granted, because the rate at which people are arriving is decreasing here, the rate at which people keep filling up this line is going down, but it's still increasing on the interval from 2 to 3. For part C on this one, we want to know at what time t is the line for the ride the longest, and then how many people are in line at that time. So let's deal with this first part of the question. So we know that while the rate is bigger than 800, there are more people coming into the line than are actually getting on the ride, so the line is growing. So the line is going to be the longest at the point at which our rate turns from over 800 to under 800. So our line's going to be increasing until r of t equals exactly 800, which happens at this point here at time 3. So this is when our line's going to be the longest, because for this whole interval, more people have been getting into the line than getting onto the ride. So longest at time 3. Now the next part of the question, now that we've answered the time piece, how many people are actually in line at that time? So we have to factor in 3 things. There are the 700 people who were in line when the ride opened. To this we have to add the rate at which the integral from 0 to 3 of the rate at which people were arriving in line. So we actually calculated this in an earlier part of this question, but we still need that integral from 0 to 3 of r of t dt. That's the amount of people who came in from over the first 3 hours. But we also have to factor in the number of people who actually got on the ride over those 3 hours. So we have to subtract the integral from 0 to 3 of 800. Okay, we have everything we need to do this and figure out the actual number here. We found on an earlier problem that there were 3,200 people who arrived at the ride between 0 and 3 for the time. So we have 700 plus 3,200. And then if we integrate 800 from 0 to 3, this is essentially a rectangle with a base of 3 and a height of 800. So 3 times 800 gives us 2,400. And we're subtracting that. So let's see here. We've got 3,900 minus 2,400. That's 1,500 people in line when it's at its longest. That's a pretty long line. For this last piece of the problem, they want us to write but not solve an equation with an integral expression of r whose solution tells us the time when there's no longer a line for the ride. So we already figured out kind of a way of figuring out how many people are in the line at any given time in part C. So we essentially have to take our work from part C, this 700 plus integral of r minus integral of 800, take all of that and pretty much set it equal to 0. We just have to be careful what we do with the variables. So we're starting with 700. We're adding an integral from 0 to t of, and now I have to be careful here, I'm going to call this r of x dx, because you're not supposed to have the same variable inside the integral as you do in one of the limits of integration. And then from that, we're going to subtract the integral from 0 to t of 800 dx. And all of this, we said, should equal 0, because when this equals 0, that means there are 0 people waiting in line. All right? Now, they did say they want an integral expression of r. And this 800 isn't technically an r, so I'm going to just change this integral over here to be minus 800t, and then we're done.